Okay, so let's get started to my final lecture. So let me start with a reminder on where you can actually find the material. So if you go to my homepage, there is a subpage called Teaching, and if you click there, you can go right into the lecture notes. So these are then lecture notes, supplementary notes, and some articles. And if you click on lecture notes, you can download, for example, the preliminary notes. And if you type in the right password, which is Weiser Berg 2018, then you can actually access the notes. And this here is really a lengthy set of notes, which is from a paper we are about to submit. And this discusses all the analysis about the two-component system in very great detail. So all the things I talked about, the detailed calculations, the ideas, the reasoning is repeated there, and you can look there and study it. And the other material I'm going to upload as, maybe over the weekend. I guess you're hiking today, that nobody will read anything today. So let me continue with the story on intercellular transport, and this was the motivating movie. So this is actual biological systems or biophysical systems where people study the motion of molecular motors along microtubules. There's quite a range of experimental data, so when you do theory, you can really cross-check this quite extensively with these kind of data and get your inspiration also from them and all the parameters, if you like, and then study it. So as you see here, there is a spiraling motion, and the question was, how would spiraling motion in concert with motion that would go straight along microtubules affect the dynamics? And to that end, we first studied a very standard model in the literature, the so-called totally asymmetric exclusion process. That's a very standard model, has been reviewed many, many times, and I try to be short in explaining what it is. So in essence, it is a one-dimensional lattice gas model or one-dimensional active matter model where you have molecules coming into the system at some rate alpha. They are getting out of the system at some rate beta. In between, they hop forward if they can. So if there is another motor in front of them, this is not possible, and this effect is called exclusion or steric hindrance, and that's the main effect that gives rise to the interesting phenomena people see. Now the way you analyze this is you can start with a lattice gas model and then do standard coarse graining, as I showed you, to go from a master equation with mean field assumptions then to a mesoscopic model. And that mesoscopic model had the form that I'm describing the system in terms of a density, rho of x and t, and this density is conserved, meaning there is a current driving the dynamics. And I wrote here j of x. The point actually is this is not an explicit function of x, it's actually an implicit function of x. It does only depend on the local density via the density, on the position via the density of the motors. This current here, J of rho, has two parts, which I call transport current and I call diffusive current. And what we found by explicit analysis is that the transport current is rho times 1 minus rho times the corresponding hopping rate. And that's actually easy to understand heuristically. So if you think yourself you are at low densities. At low densities, this is just the velocity nu times the density, so the standard expression. And then the exclusion effect that I noted here, this reflects itself in the term 1 minus rho. The diffusive current is as usual. This is just minus the gradient in the density. So that's the story about how you come up with the equation of motion. The next step, of course, is how do you analyze it? How do you see what kind of density profiles you get, what kind of currents you get, and how does all that depend on the parameters of the system, meaning the entrance rate and the exit rate. And I will not, yeah, go ahead. No, not in that case. So if you do the analysis starting from the lattice gas model, the diffusion constant here actually turns out to be a half times nu. Okay, so the question I just phrased was, how do you go from an equation of motion to a corresponding phase diagram? And there's various ways of doing so, and I'm not going into that because I want to focus in this lecture on this structure. How do you get to the equation of motion, and how do you get to the current, and how is this current you get for these kind of systems different from that, and how is additional effects to exclusion playing a role there. So let me be short in discussing the phase diagram for this particular system. And what you find is the following. You find that as a function of the control parameters, now being the exit rate and the entrance rate, there is some threshold values given by a half. And these threshold values given by a half, they define phase boundaries. So let me draw it. There's a line like so, going to a half, and then there's two lines emerging here, such that now let me give the names here. There's a maximal current phase, there's a high density phase, and there's a low density phase. The ways you arrive at that is through either what's called kinematic wave theory, and that goes back to Lighthill and Whittam. Or if you have understood kind of the physics of what's going on, you can formulate an extremal principle. That was done by Joachim Krug, I guess, the first time. And this extremal principle is one on the current J, and it states under what conditions, if the left and right densities are larger or smaller with respect to each other, you find the maximum value of the transport current or the minimum value. So that's how you would arrive at the phase diagram. But actually, even without, it's pretty intuitively clear of why you get such a phase diagram. So just put yourself in this situation, and now I'm arguing heuristically. Here in that window of the phase diagram, the entrance rate alpha is actually larger than the exit rate. And if the entrance rate is larger than the exit rate, you can think of a system where lots of cars coming in, and at the end of the road there's a green light, so you can accommodate with a pretty high density in the system. Right? That's why you have a high density phase here, and the bottleneck that determines the current and the density is how much you let particles get out of the system, and beta here is the exit rate, so the density which will adjust itself here in the high density regime is check this right, is one where it's determined by the exit rate. This is the other way around. So in that situation, you have a low entrance rate and a high exit rate. So you keep the green light and things can move out, but you driving the system with lots of particles coming in, with the particles coming in. So here the limiting factor is how much particles you supply, and that means the density is determined by alpha, and the current as well. The current is then just given by alpha times 1 minus alpha. And here in that regime, you are having alpha and beta so large that the system doesn't really care about the boundaries. And then what happens in your system is that if I draw here my current density relation with 1, a half here and a quarter, the system then tries to accommodate the maximal current it can possibly have. So in this regime here, you're right at this point where rho is roughly equal to a half, and the density is maximal given by a quarter. All right, so that's the kind of main summary of this one-dimensional transport model. And what I'm going to do is now I'll focus on what happens to the relation between the density and the transport current in a less trivial model than this one. So for that, this was the system we looked at. And now the way you can imagine this in a cartoon-like fashion, if you have now a microtubule, this is a cylindrical structure with something like 13 to 15 individual lanes, also called protofilaments. And along these lanes, you have different types of motor moving. One situation is that you have kinesin 1 and kinesin 2 moving along those cylindrical highways. Kinesin 1 is moving on a straight track, so in green here, and the kinesin 2 is moving on a helical path. And now let me formulate the model for that. All right. Okay, so we take this picture. You have at the left-hand side of your system some kind of reservoir supplying the particles to the various lanes in your system. The number of lanes, which way around do I do it, are W in number. So for example, here I have 1, 2, 3, 4, 5, 6 lanes, and in general W is the number of lanes, and the index I will use for the lane is index I. Now there's various lanes, so let's put down just the first lane and maybe also the second lane. There's lattice sides here going from 1 to L, and the index I'm using for the lattice side is going to be mu. There's two kinds of particles. There's one type of particle which is just the usual particle of this T-sep type. It hops forward along the lanes, just a single lane I, and I call the corresponding rate nu t for T-sep-like particles or track keeping particles. And there's a second type of particles, and let me indicate them with a color. So this type of particle here, and that type of particle is not moving straight, it's actually moving along the diagonal with a rate nu s, s being for spiraling or switching motion of the particle. So you have two types of tracks. One is going along the diagonal, and the other one is going straight. So in addition to these internal dynamics, you also have a coupling to the reservoir, and this coupling is as before. There is particles of the S and T type in the reservoir, and here you can fill the first side on any of the lanes with the corresponding rates alpha S and alpha T for straight moving and for switching and tracking particles. On the other side here again you have a reservoir for particles hopping out of the system, and this can happen at certain rates, and they are denoted by beta S and beta T for the corresponding two types of particles. Yeah? Yes, that's true. And that's a whole nother paper. I mean, we have written a paper on that quite some time ago together with Andrea Parmigiani and Thomas Franosch, where we asked ourselves, how is the TASET model modified when you add on off kinetics? And it is actually modified quite a bit. So instead of having these three faces, there's a fourth one where you have a domain wall appearing between two faces, and the domain wall is stationary. All right, so it modifies it, and this is certainly the simplest model we can think of. In the paper, which I mention in a minute, we have studied also what happens as you add that, and it turns out that for a certain regime, which is reasonable biologically, you can actually have it robust in terms of the effects I'm getting here. No. So in a cellular system, the way you would then analyze it is really that you have a cytosolic volume. The cytosolic volume has a certain density of particles. They can attach anywhere with the same rate, an on rate, maybe particularly at the left end, but it doesn't really matter since it's a measure 0 point. And the off rate, of course, is different from that on rate because there's some special biology going on at the end of a microtubule that's not as blunt as I drew it here. It's actually a pretty rough kind of edge, and there are special effects. Okay, so this is certainly an idealization I'm taking here in order to make the model accessible by analytical analysis, and then you can add bells and whistles to that to see how things change. You can, definitely. And people are doing it. There's a recent paper from Stefan Dietz's group in PNAS, just came out a few weeks back, and they specifically study that. And if they, tweak the parameters a bit, I think they can also study this kind of behavior. And there's other people who try that. It's not so easy, right? You have to have a microtubule which is freely suspended. Otherwise, this is attached to some cover slip, and that messes up the motion because you get stuck at the cover slip. So you have to suspend this between two properly designed barriers and then look at freely suspended microtubules. And as this is, or you can modify it and study a modified model so that there's a way of directly comparing this with experimental data. Okay, I want to focus on how this deviates from the TASET model and what new physics comes out of it. Other questions? Yes. Yeah, you could make them move at some other angle. Doesn't really matter that much. Actually, there's symmetry. If you relabel the particles, the straight moving ones can be made into diagonal moving ones, and the other ones into straight moving ones. Yeah. The essence is that they cross path. And that's giving rise to what I call topological hindrance in contrast to steric hindrance. So in steric hindrance, if you're somebody ahead of you, it blocks your path. If you have things moving along different lines, then you can create larger regions in space which are not accessible because you block them in terms of the topology of the path. All right. Go ahead. not necessarily. You can study L over W anything. It's actually interesting what happens as you increase W. You're going to see. All right. Other questions? Well, that's the model. And now you have to analyze it. And the way you analyze it is you just proceed in the same way as before. You define occupation numbers, and these occupation numbers then indicate whether at lane I and side mu a particle is sitting or not, and at what type it is. Is it switching or is it track keeping? And you just have 0 or 1, so you look at a exclusion model where you don't allow occupation of more than one particle per site. Yeah, so one type of particle. Yeah, so if an S is sitting here, or say an S is sitting there, this T cannot move towards this site. Right, and that's what's reflecting the biology, because these particles are attached with their molecular heads to the tracks of the microtubule. So once there's one kinesin motor sitting there, nobody else can go there. Good. And I want to arrive at a hydrodynamic theory where I, instead of looking at the occupation number, I want to look at the corresponding densities, and these indices then should turn into some, say, variables y and x being along or perpendicular to the track. Now let me write down the equations of motion for that. The equations of motion they are just inferred by the same kind of idea as you have them for the TASEP. So let's write the dynamics of a particle which is of the type moving along a track. Then there is contributions coming in and out. So what's coming in? So you can have, with a rate nu t, that's the rate by which those particles move, you can have it move from a site mu minus 1 at lane I to a new site at site to the site mu. Okay, if that site is actually empty, and I should not write any index here because this is strict exclusion, so if anyone is sitting there, it will exclude the motion. So Ni mu is the sum. Go ahead. Right, that's a total number, or the total occupation number. Right, this is the in process, and there's a corresponding out process. And I guess you can easily guess this. So if the site I mu is occupied and the site ahead of it is empty, so 1 minus n I mu plus 1, then you lose a particle by forward hopping. All right, so let's write down the equation for the S particles, and I erased that. I hope you have this. To write down the equation for the S particle. So dTt n I mu of the S particles, that's happening with a rate nu s. And then you have diagonal motion. So you want a particle starting out at lane I minus 1 and mu minus 1 to arrive at the upper diagonal site, which is then lane I and track number and along the track number mu. All right, average, and you lose something if you start at this particular site with an S particle and you move up in a diagonal fashion to this point here. All right, that's the way to view it, and now let me rewrite that in terms of currents. So maybe I go here with my board. So what is that? So if you write this here in terms of currents, now we have to have a convention of how we want to index the currents, and I want to index the current here as the current going into the side I mu. So this I call then the current Ji for t mu, so the current going into that side minus the current that goes into the side ahead of it. And similarly here, if you want to write this in terms of currents, this is the current going into the side I mu and the current leaving into the side which is along the diagonal one up. So you can read this as the current balance, current going in and current going out. And there's another set of equations which apply at the boundary. And I don't write them down because I won't need them for what I want to teach you in this lecture. But of course, you know, if you go close to the left end at 1 or close to the right end at L, what I wrote here is not correct, because then you have particles hopping into the system or hopping out of the system, and it's the same way you figure that out. Now I'm also going to simplify to the case that nu t equals nu s equal to 1. I can choose one of the time scales, of course, that's up to me, but the second time scale, choosing that equal to 1, is a special choice. And you can study the general one for yourself, but it turns out that phenomenologically you get the same kind of behavior, essentially. All right, so now let's ask the question whether you can go from here and do what everybody does in the field, namely do a mean field theory. Would that work? Because that here, right, this isn't on the board anymore. The TASEP model and the simple current density relation relied on the fact that mean field theory works and correlations are unimportant for the transport. That's my main question now. How important are correlations for the dynamics of my system? Well, for that I need to tell you what the outcome is if I do a mean field theory. And you can read this off. So mean field means all the right-hand side expressions, I'm going to break them up into products of averages. And then you can write down the current. So we just follow me with that. So let's say I want to write the total current, J mu, which is the current on the lane S plus the current for the particle type S and the current for the particle type T. And as you might notice, I left out the index I. And that's because I have in the steady state cylindrical symmetry. So if I have the average current, it cannot depend on the index of the lane. All right, so now let's write down what this is in terms of mean field theory. We just have to break up these brackets and add those things up. So let me write each current separately. So that's R mu minus 1t times 1 minus R mu, rho mu, for the current of the T particles. So the other way around, to not confuse you. And then rho mu minus 1s, 1 minus rho mu. Very simple, but now as you add this up, you see that this and this adds up to rho mu minus 1, 1 minus rho mu. So it seems that things are super trivial because you arrived at the very same expression as for the Tay-Set model. Okay, so mean field just says, or would predict, that this is equivalent to a Tay-Set model, and it doesn't really matter whether you have two different particle types and how many you have of the respective particle types, right? Yeah. Yeah, but you could then say, well, I have a closed equation for the total current, and all I care about is the total current. I don't care about the individual currents. And then this should be not so interesting. Yeah, but in that case as well, you have predictions which are mean field-like of a similar type, and they turn out not to be correct. Okay. Of course, I'm simplifying here. So now let me show you what actually happens. Oops. So what actually happens is this. The total current, if you measure it by a standard Gillespie type of algorithm, so you do the stochastic simulations, shows this kind of outcome. And there's two features I want to point your attention to. One feature is that the total current is not going up to 1. It's actually, the total current becomes 0 for some earlier density. So at some maximal density, game is over. You cannot fill particles anymore into the system. So there should be more than just steric exclusion, because steric exclusion means that you have a factor 1 minus rho. So there must be more than that. And you'll see this is due to the topology of the network of the stochastic process. That's one piece of information. The second piece of information is that the current is not just a function of rho, it's a function of an additional variable. And this additional variable is delta here. And let me later write it on the board. So delta is essentially the ratio of the entrance rate for one particle type, namely the S type, versus the entrance rate of the second particle type, namely the T type. So changing the relative amount of particles of S and T type you have, you will get different kind of behavior. And as you see here from this plot here, where the species fraction, so alpha S over alpha T, is plotted as a function of density, this maximal current is really something which drops down rapidly as soon as you put in minute amounts of other type of particles. So it's not a function which goes in here smoothly and then goes up again, really drops down dramatically as soon as you put in some minute amount of other type of particles. And there's also, if you notice, a mirror symmetry. So delta and 1 minus delta is the same, and that's just because I can relabel the particles being S or T, and that gives the same outcome. So for now, you can look just at one half of it and study what happens. What I would like to explain is why is that so? What's going on here? Why is there a gap? And can I actually calculate the current density relation by taking into account, well, what do I need to do? I need to account for correlations, because that's obviously must be some kind of correlation effects. And that's always non-trivial, because the way you take into account correlations could either be through some hierarchy, through some next nearest neighbor arguments, and so on and so forth. And that's not working here actually. What you have to find is some more strong coupling type of approximation that accounts for this behavior. All right, so maybe I also show you a movie so I don't have to change this too much again. So this here is a movie. Come on, move. Which is a poor man's movie, I would say. So what you see here is a simulation of what's going on, and then the system is stuck, and you can kind of see also why it's stuck here. So if you think of this particular situation where you have just two lanes, you see if there's some guy sitting here, then this particle is blocked to move in that direction. So this whole row here, these two sides are empty, and they leave the lattice much more sparse than you would have if you don't have these crossing paths. And if you go even further and look at a simulation like so, where you have many lanes, this was an initial state where you had many particles in the beginning, then as the system equilibrates to a non-equilibrium steady state, you see actually because of that steric hindrance and the ensuing, exclusion of a whole set of locations, the actual steady state in the end is a very, very sparse state, and there's not many particles in there. You see here there's a blockage of those particles for these here, and there's a blockage in the other way as well. Okay, and that's what we want to study and understand. All right, we go back to the board. So the first observation we make that there is a maximal density rho max which supports the current. Above rho max there is no current. This is by itself actually a non-trivial stochastic processes problem, how to figure out that. And the way you can think of this is you imagine that you turn off beta. So you don't allow anybody going out. So well, then it's like you turn your model upside down and you fill it with particles, and some of them are allowed to fall straight and the others have to hop diagonal. So it's a filling problem, how you can fill up a lattice of particles with particles that move along different paths, and then you end up with a explicit expression for that. And you can do so. So if you do the analysis of the model, so this filling problem, and let's say we take two lanes, W equals to 2, and we take the symmetric case, then what you find, I hope I get this right here. Yeah, I'll write this down in a second. So the delta equals alpha s over alpha t. Why is this significant? Oh, sorry, I've had it wrong. Sorry. You're right, as always. Alpha s plus alpha t. Okay, so that's my delta. It's the fraction of the two particle types. Right? So so you can solve this filling problem exactly And if you now study a particular path of the system, so you're plotting here the density rho as a function of t in your stochastic simulation, you can calculate this value here, rho filling exactly, and I forgot what the exact number is, but I have it in a second. So this is 0.79, and as said, you can get this from a not so trivial stochastic processes problem. And now let's look at a trajectory. Oh, yeah, yeah. It's an eigenvalue problem with transfer matrices where you have to define a proper state space of how you fill up the lattice, and then the solution of the eigenvalue problem coming from that gives you this density. I don't have time to talk about this. This is way too technical for now. So if you follow a typical time evolution of a system, it will actually reach this filling density, but then because an actual system doesn't actually have a rigid boundary where particles cannot move out, they can actually move out. And now as you move out, if you think about the filling problem, in the filling problem there are some loose particles, right? If you stop at the right-hand boundary and you have a situation where there's particles which are somehow loose and not fully jammed, they can then move out if as soon as I allow the system to open and particles to flow out. So what actually will happen, it will go slightly below this filling density and then arrive at some kind of jamming density rho max. And this rho max you can actually then also calculate, now not exactly but approximately. So with some further calculations you figure out that this is 0.74 theoretically, and the experimental value, meaning the simulation value here, is 0.73. So you get pretty close. Yeah. Who's first? This depends on W, it depends on delta, it depends on this doesn't depend on beta. This value. As soon as you have a finite beta, you drop down to this value. So beta just allows you to hop out. I'm asking not how the whole profile looks like, I'm just asking what is the maximal density I can possibly achieve. And that's independent of the value of beta. So this value here is the value of beta equal to 0, and this value is here if you have any finite beta. It's the maximum value I can have. Yeah. Yeah. You mean the symmetry of particles and holes of the same type? So I can look at holes going from right to left. I think it's because that you have a jamming density, rho max, which is not equal to 1. That's ultimately the reason why you don't have this mirror symmetry anymore. Yeah, yeah. And if you think about what happens at the jamming point, if you add or remove particles, they have different effects. So if you just add an additional particle, it doesn't matter at all. And if you remove one, this can have a big effect. Right? So it's a difference in adding and removing particles. Other questions? All right, so what I'm just saying here now in the end is there is a rho max. And you can figure it out. And actually, you can even calculate, or guess, I would say, what happens with rho max as a function of W. And rho max as a function of W, it turns out that this approximation here, where I'm saying that every filling of every lane, every column is equally likely. Okay, so this is what this says. If I assume that every type of filling, 1, 2, up to W, is equally likely for a particular row, then I get this expression, and this is just the harmonic number, and this converges in the limit of large W to an expression log W over W. And that means that the rho max is really rapidly decreasing as a function of W. And you can check this function here with experimental data, meaning simulation data, and they are more or less on top of this expression. I don't really understand why, but that's this naive maximum entropy argument somehow works. Yeah. For microtubule, it's 13 or 15. That's known. It depends on how you prepare the microtubules. If you prepare them carefully, they are 13. And for 13, I think it's the case where they don't have a seam. So I can actually have it like so. If you have different lane numbers, then there's a seam and there's a problem of how the particles actually move when they hit the seam. Yeah. Yeah. That's a whole set of problems. I mean, people have looked at TASEP and what happens in TASEP if you add slow sides and fast sides, so defects, and it has an effect, right? Because you're creating slow sides, and those slow sides then change the current. They lead to a lower current, and if this lowering of the current is significant, you can actually have traffic jams because of the defects, right? Yeah. Well, this TASEP problem has been studied really at length. You know, if you look at the literature, there's one lane, there's two lanes, there's things moving back and forth, there's defects, there's many defects, so this is studied well. All right, so this is my main point. There exists a rho max, and now we have to think about what's the implication of the existence of a jamming density, and can we infer from that very phenomenological effect the current density relation. That's what I'm going to spend the rest of the lecture with. So I call this theory of topological hindrance. The way you should look at this theory is really in the spirit of this Lighthill-Witham theory or any kind of macroscopic theory where you start from a macroscopic relation. So you claim there is some form of the current density relation, and you try to find some semi-phenomenological arguments to actually explain the corresponding current density relation. So let's start from scratch. So let's start writing down the current for one of the species, here the spiraling species, and we had this on the board here. So this is, you start from that side, you move along the diagonal if it's empty. All right, so that's the expression, and you can rewrite that expression in a different form, namely you say you split off what is the mean field solution. Yeah, That's what I do. I look at the steady state. Thanks for asking this. I'm not trying to analyze the whole approach to steady state. I'm looking at the steady state. So at steady state, and I guess the reason you were asking is I'm having again the index I missing, and this is because in steady state I have cylindrical symmetry, and cylindrical symmetry then allows me to do that. And it allows me also to just argue with the currents alone. Well, so what I said is I split off the part which just is the mean field part. And in order to be correct, this has to then have a correction term, and the correction term is the covariance, but let me write it out. It's the correlation function of the occupation number of particle species S with the total occupation number minus rho mu minus 1s rho mu. Okay, so this is the covariance of ni minus 1 mu I minus 1s ni mu total number at the site. Okay, you can do the same thing, of course, for the other expression, so for jt, and I'm not writing it down, so that's really analogous. So for j mu t, you get a similar expression, and now we want an expression for the total current. So, well, the total current, J, the sum of the two, is then equal to, and let me write it out, rho mu minus 1 minus h mu minus rho mu, and h mu is defined as something divided by rho mu minus 1. This something are the covariances. So this is the covariance of the S particles plus the covariance with the corresponding expression for the T particles. Okay, so now we do have a relation which looks simple again, but just because I wrote it so. Right, this h of mu, which I call hindrance function, or if you like also the covariance function, this is hiding all the interesting physics because it's hiding all the correlations of the problem. Now, if I go to a hydrodynamic approach, my task is to actually infer that quantity. Okay, and at first, the way you would write it down in hydrodynamics is to say, well, J then is a constant, and this J is rho of x 1 minus h of x minus rho of x. Okay. Now in steady state, J is a constant. That's the nature of a steady state. So it cannot depend on the position explicitly. The only way it can actually depend here on density, on position, is via the density rho of x. Okay. So what I have is again a relation J of rho, which is rho 1 minus h of rho minus rho. And of course, I'm hiding something here. I'm hiding here that this rho, or j of rho, is more explicitly a function of this type. So this j is a function of rho, and the rho depends on parameters which are characterizing the dynamics of my system, and it also depends on the delta. This is something you can either check numerically if you like, and it's true. If you check it numerically, heuristically speaking, there must be an explicit dependence on delta, because that's the nature of the problem. The fraction of the particles switching the lanes is important. It's explicit and determines the currents. And here, if you talk about alpha and beta, those are intrinsic parameters that determine what the density will be, and they will, heuristically speaking, only affect what the density will be and not what the current will be. And the beta actually, which I wrote here, is a special beta. It's the average of the exit rates. So I can define an average exit rate, which is the fraction of the s particles times the exit rate of the s particles plus the fraction of the t particles times the exit rate of the t particles, and then beta is given by 1 over this mean exit rate. And alpha I just took as the average, or the sum of the two rates. Now, well, how will we get the function h of rho? How do we infer that by analysis? And this is best understood if you look with me at what we find from the simulations. So here we have the reference curve, which is the Tay-Sachs curve, where the current J is maximal at a quarter and runs between densities rho equal to 1, from 0 to 1. And now the actual current density relation is like so. You have a maximum value coming from this filling problem, and you still have a maximal current here. The shape here is very similar to the shape of the Tay-Sachs curve. It's, if you like, just reduced and pulled back. And now the way you can think of this heuristically or semi-phenomenologically is, can I somehow understand the physics in this part and in that part? Can I somehow understand what the correlation effects are to the right and left, and then do a Taylor expansion such that I infer the slope of that curve here and the slope there, because the rest I know the value here, it must be 0 at 0, and it must be 0 at rho max. So if I somehow find an argument that gives me the slopes, I can infer at least how this curve goes up here and how that curve goes up there. Yeah? Why should I? You mean it's perfectly parabolic? No, it's not. It's not. Okay, it's not. It's almost. So, and actually, I'm using this. So what I'm saying then here, if you have some linear function, then these linear functions, they will come here together in a cusp, right? So that's not nice, but I actually know that this has to be some maximum value here. So I'm using a matching condition up here and say to second order, I need to have a maximum here, and that determines the maximal current position right here. So I have three conditions. One where I need to figure out the physics to the right and left, and another one where I say I have to have a maximal current and I have to have a parabolic profile in the middle, and that's my third condition to get the hindrance function h of rho. Okay, so from that I'm trying to get this h of rho. Clear so far? All right. So let's go into the argument of how do we get the h of rho, and let's just proceed through the various cases. And I'm starting out with the case that the density is very small, so I'm at the corner to the left. Okay. So try to infer h of rho at rho going to 0. Well, the first trivial fact is that h of rho at rho equal to 0 needs to be 0. So I only need to ask myself, how does the current change in the vicinity for rho being small? What is that? Well, let me try to illustrate how this works. So imagine that you put yourself somewhere in this lattice. So let's say I'm in this lattice somewhere. And there are all these different sites. And I'm now picking a site, let's say this one. And I'm adding a particle, adding mass to it. What will happen? So intuitively, two things can happen. If you add a particle here, it blocks motion to the left, but it adds current to the right. So let me first look at how it reduces the current. Okay, so let's look at current reduction. And the way this works is you just look at the various cases possible here. One case is that you do have a particle of the type that's moving along the diagonal here to the back. It's blocked, right? It cannot move. But you don't have a particle here at this site. And the other cases are you have a particle here, but none there, or you have here a particle and there a particle, because they're the only options that are affected by the mass I add here. Okay, so let's look at that situation. In this particular situation, the current change is negative, so you're blocking something. The probability of having a particle occupied here is rho s. Well, I'm using something here now. What I'm using that I'm at rho small, and things are uncorrelated. Otherwise, I couldn't argue that there is some density here. I would need to worry about correlations. So there is a probability of finding that particle here, and I assume that the case I'm looking at is that there's none there. So that's the reduction of the current for this situation. And the other situation is just analogous. You have a particle T and no particle S. And the final case is you have rho S and rho t. So that's a current reduction. And you can also think about current enhancement. So here. And now I'm looking on the other side towards the right of this picture. And there the current can only go up, of course, if the place I'm trying to reach is empty. So that means any contribution I will write down here will always have a factor of 1 minus rho. Right? Now I can have different situations. So for example, I can fill that site here with a particle of the type S, say, right? Then the probability for that to happen, and I hope I get this right now, is delta. Okay. So that's, I'm filling this particle here with a S particle. And then I need to have, for the various choices, the different cases, one where, say, the neighboring particle here is a T particle, so it doesn't compete for the current. That's the first case. So I have one contribution, delta, so filling this particle with a S particle, the other one not competing, times an empty site. You can do the same thing here with filling the particle with a T particle, then an S particle not competing, 1 minus rho S and 1 minus rho. And then you have a situation where you actually have both particles there. Then the corresponding expression that you get is delta 1 minus delta rho times 1 minus rho. So that's in total what you get. And you can sum this up, all these different contributions. And let me check this out of what this was in the end. So this dj d rho then turns out to be 1 minus 2 rho 1 minus delta 1 minus delta times rho. And that gives me the slope of j of rho at rho equal to 0, and with that also, of course, the slope of h of rho at rho equal to 0. And you should notice that this contribution is, as it must, symmetric in interchanging delta with 1 minus delta. Otherwise, I would break my symmetry of exchanging S particles with T particles. So what about the other end when I go to rho max? Yeah. Whatever they are, I didn't try to calculate them. You can. You can. I mean, I trust this argument. Of course, these arguments are as all. Yeah. They actually are. Well, in the vicinity of this point here, you are in the almost uncorrelated case. So what I'm adding here is small correlation effects, and I don't really see that this stops the expansion. So all I need here for my argument is the derivative of h at rho equal to 0. Right? That's all I need. I don't even need to go to higher order, because the higher order I get for free from this argument that I want to match the two here at the top. I'm sure you can work harder and try to find second order corrections. I'm just not able to. So what you get here is from that here, you get h low density prime at rho equals, I think, delta times 1 minus delta. Yeah, is delta times 1 minus delta. That's what you get. Now, the other question is what happens at rho max? And at rho max, um, there is a difference because now I'm in the limit of very, very strong correlations. I'm close to jamming. So now, how would you argue in this case? Is there a way close to jamming to actually enhance or and reduce the density with this argument? So if you fill something in a jam configuration, you will not add a thing, right? This will not add to the current. So all you do in the vicinity of a jammed configuration is you actually reduce the current by adding something in. And all you do is essentially, if you look at these expressions here, that you can just redo the same arguments, then you get expressions which look like minus delta rho max times 1 minus delta rho max. So this expression here is the fraction of S particles at maximum density, and this T here is then the fraction of T particles at maximal density. So that's all you will get in this case. Fridtjof. We did. Yeah, and that the point is that I'm leaving the strong coupling limit here is that I'm leaving this out. I'm kind of saying that the jammed configuration, there are infinitely strong correlations. So I will never have any kind of addition of current. I just lose currents. And the assumption is that the density everywhere is rho max. This is an approximation. This is not exact. Yeah. Mhm. Yeah. 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 And that's the expression you. Yeah. So you can argue the other way around if you like, for sure. Yeah. I'm kind. Yeah, I'm kind of waving my hand here. Yeah. 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 So at the low density, I'm fine because I can use the assumption that things are uncorrelated and I can argue with densities. Here I'm a bit, hand waving and saying, well, this is gone, this is there, and I need to put rho max in order to make sure that things are right. I would be, I would not trust my argument anymore because it has to be right. You're gonna see this is really good. Should I show this now? Yeah. Yeah, of course. I mean, that's actually kind of the whole story because the rest is trivial algebra. So once you know these expressions at the two limits, so here and there, you just need to add the analysis of matching this horizontally at rho MC, and then you have everything together. So let me show you what the actual expression is without writing the um, the analytic expressions. Yeah, you have enough conditions to determine that. All right, you saw that. And here actually, this is what I plotted. This is my wild guess on, or Patrick's and Emmanuel's wide guess on what the maximum density rho is as a function of the number of lanes as obtained from this maximum entropy argument, and you see it's pretty good actually. Yeah, so I'm kind of shocked. It's an open problem, I would say. So if somebody of you guys has an idea of make this more rigorous, it would be actually fun to learn. What's significant is, look how this is going down. So this will give you a pretty empty lattice in the limit of w going to zero, going to large values. So this jamming effect can be really, really strong. All right, now let me show you how good this whole ansatz works. And here we go. Right, so this green, blue, and orange points are data points Patrick and Emmanuel obtained from their simulation studies. And the dashed and dotted lines, they correspond to the corresponding analytical expression obtained with this type of reasoning for a different number of lanes. So 1, 2, 3, 4 lanes. And you see it's working great here at the left end. It's a particular case actually here. This is for delta equal to a half. So the slope is actually the same for all of them. And well, here at the right-hand side, John, I don't know, this looks okay to me. It's not quite right, so it misses, I guess, the details, but it's a pretty good approximation. And here, fitting it in between, it's also not quite right, but it's giving you a good idea of what's going on. Yeah. So it's bending this way. So this one. What do you mean? To the right. This stops here. This is rho max. Well, I calculated the slope, and it's minus delta 1 minus delta rho max. So depending on the value of delta, it's always negative, right? It's always negative. Delta is a half here. So this is minus a quarter times rho max. And rho max is whatever it is, so it's 0.7 something. Yeah, that's what it is. Yeah, it's a negative slope. All right, that's what you get. Other questions? Yeah, you make a quadratic approximation. So he was asking, is this quadratic? Yeah. Right. The linear part of the parabola I get from the slopes at the right and left end. Sure. That kind of parabola. Yeah. Yeah, so I'm fitting a linear and a square part. The linear part I'm getting from the physics at the two boundaries, so at the boundary where there's no correlations and the boundary where there's maximum correlations. And the quadratic part is, I'm fitting it, right? The quadratic part contains the assumption of the existence of a maximal current, and then I'm done. And you see it's not quite a parabola. There's deviations from it. Yeah, but it's quite close. So I would say this type of reasoning is very similar to this Lighthill-Witham approach, where you just guess a function of j of rho. And what Emmanuel and Patrick have been succeeded in doing is that they found a way of calculating this function, calculating the correlations without really calculating the correlations. So now the point remaining, and that's something I really don't have the time to dwell into, is how would you then use this information to map it back to a phase diagram, right? I'm still having here a current density relation, and I need to say how would I, as a function of my average alpha and the average beta, draw the phase diagram? There's no surprise in terms of that we'll get the same topology of the phase diagram as TASEP. You will get a low density phase, you'll get the maximum current phase, and you get a high density phase. Where those phase boundaries are is a tricky issue, because for that you need to worry about the correlations at the two ends of your lane. So you need to work out the correlation effects at the right and left end to map the entrance rate and the exit rate to the corresponding currents. And I spare you of that. If you want to read about this, this is in this paper which got out recently by Emmanuel and Patrick. So it's Patrick Wilke, Emmanuel Reitman, and myself, and this is a recent PRL from, I guess, last week, a PRX of last week. Now, let me conclude with a few sentences on TASEP-like models. They have come into years. I mean, this has been invented long time ago. But actually nowadays, they are used as quite interesting and informative models for understanding transport of molecular motors along microtubules. You can use them quantitatively to really explain how different motors, they have different names, I don't want to name all these different terminologies, and you can really quantitatively explain how these molecular motors move on microtubules, what the effect of steric exclusion is, what the effect of pausing is, what the effect of attractive interaction is, and et cetera, et cetera. This works out quite nicely. And if you like, I can point you to the literature. What's useful, I think, from a more theoretical perspective is that you can use these models in a way that you largely solve most of it analytically. And especially here, I guess you saw that this has some advantage because it helps you understand what's the underlying physics of the problem and what's going on. Now, moving forward, if you look at this special problem here, now I feel this type of problem comes closer to 2D active matter. It's still quasi 1D because you have this motion being restricted according to certain lanes and certain gates of motion, but it's for as large a lattice as you would like in the transverse direction, and it includes now phase behavior which hasn't been seen before, namely jamming. And actually, if you look closer, and that's something I didn't explain as well, there's actually pattern formation. If you look at these patterns in a certain parameter regime, you see density modulation, which is absent in a standard TASEP-like model. I'm putting your attention to this. We call this topological hindrance to distinguish it from steric hindrance. And the idea is that if you think about the system in terms of a high-dimensional space of stochastic process where you have certain allowed routes and disallowed routes, the way this is affecting the dynamics is that a certain set of sub-routes in that networks are disallowed, topologically forbidden, if you like. Or in other words, there are correlation effects which affect the dynamics. And I guess this hindrance function is just one phenomenological way of trying to figure out what's going on in these systems, and I'm looking forward to other approaches where people figure out more about what correlation effects could be in these kind of TASEP models. So with that, if you have questions, still ask them, yeah? No, not yet. This is something we try to convince our colleagues of, and our best, guess is Stefan Dietz from Dresden. He actually did the experiments with these kind of motors, and they have the setup. So we could actually try and work it out with them. There are some additional effects, as we discussed, right? The real motors detach and attach, and they don't follow a straight path. They sometimes have the freedom to actually wiggle off from a diagonal path or a straight path. So the effects will be not as clear as we see them in this asymptotic model, adding those effects still gives you a similar phenomenology. So I'm pretty confident that people will be finding those predictions. Yeah. Yeah, Sean.
So you've been able to extract the correlations of sites that are right next to each other, either horizontally
Yeah.
or diagonally. Do you know anything about the long-range correlations of these structures?
The
I'm
kind of
asking that because if you looked at the
yeah.
simulation, you saw these long sort of blocked channels running diagonally through the
Yeah,
structure.
the way you put in the long range correlations is by the existence of rho max. And this is a separate problem, right? The separate problem is that there is a maximal filling fraction of the system.
No, no, I'm just asking, could you calculate by these sorts of approaches the correlation of the density, say, of widely separated points?
No,
Do you
no.
think there's anything interesting there? Do you think there could be
For sure there is. You saw it. I mean, this is,
right, exactly,
you saw it. This has plenty of correlation effects.
right, right.
And there's questions you can ask, what's about the counting statistics? Like, you know, what's the kind of noise you get of particles getting out? Is this shot noise? Is there some correlations in the noise? People have asked those questions.
Simple correlation.
Yeah, in how things move out, because you see this kind of avalanche type of behavior, how things get out. And
And you're saying right now you can only get at that through simulation.
yeah, that's only through simulations. I don't know how to do it analytically, but maybe somebody here knows. All right, so thanks for your attention. It was a pleasure.